In this example, we will see linear regression. But before we start, we need to define a multivariate and univariate normal distributions. The univariate normal distribution has the following probability density function. It has two parameters, mu and sigma. The mu is a mean of the random variable and the sigma squared is its variance. Its functional form is given as follows. It is some normalization constant that ensures that this probability density function integrates to 1 times the exponent of the parabola. The maximum value of this parabola is at point mu, and so the mode of the distribution would also be the point mu. If we vary the parameter mu, we will get different probability densities. For example, for the green one we have the mu equal to -4, and for the red one we have mu equal to 4. If we vary the parameter sigma squared, we will get either sharp distribution or wide. The blue curve has the variance equal to 1, and the red one has variance equal to 9. The multivariate case looks exactly the same. We have two parameters, mu and sigma. The mu is the mean vector, and the sigma is a covariance matrix. We again have some normalization constant to ensure that the probability density function integrates to 1, and some quadratic term under the exponent. Again, the maximum value of the probability density function is at mu, and so the mode of the distribution will also be equal to mu. In neural networks, for example, where we have a lot of parameters, let's denote the number of parameters as d, the sigma matrix has a lot of parameters, about d squared. Actually, since sigma is symmetric, we need d times d plus 1 over 2 parameters. It may be really costly to store such matrix, so we can use approximation. For example, we can use diagonal matrices. In this case, all elements that are not on the diagonal would be 0, and then we will have only d parameters. An even more simple case has only one parameter. It is called a spherical normal distribution. In this case, the sigma matrix equals to some scalar times the identity matrix. Now let's talk about linear regression. In linear regression, you want to fit a straight line into your data. You fit it in the following way. You want to minimize the errors, and those are the red line is the prediction, and the blue points are the true values. And you want somehow to minimize those black lines. The line is usually found with so-called least squares problem. Our straight line is parameterized by weight vector w. The prediction at each point is computed as w transposed times xi, where xi is our point. Then we compute the total sum of squares, that is the difference between the prediction and the true value squared. And we try to find the vector w that minimizes this function. Let's see how this model works from the Bayesian perspective. Here is our model. We have 3 random variables, the weights, the data, and the target. We're actually not interested in modeling the data, so we can write down the joint probability of the weights and the target given the data. This would be given by the following formula. It would be the probability of target given the weights and the data, and the probability of the weights. Now we need to define these two distributions. Let's assume them to be normal. The probability of target given the weights and the data would be a Gaussian centered at the prediction, that is w transposed x, and the variance equal to sigma squared times the identity matrix. Finally, the probability of the weights would be a Gaussian centered around 0 with the covariance matrix sigma squared times identity matrix. Alright, so here are our formulas, and now let's train the linear regression. So we'll do this in the following way. Let's compute the posterior probability over the weights given the data. So this would be probability of parameters given the data. So those are y and x. So using the definition of the conditional probability, we can write that it is probability of y and w given x over the probability of y given x. So let's try not to compute the full posterior distribution, but to compute the value at which there is a maximum of this posterior distribution. So we'll try to maximize this with respect to the weights. We can notice that the denominator does not depend on the weights, and so we can maximize only the numerator. So we can cross it out. Alright. So now we should maximize the probability of y and w given x, and it's actually given by our model. So we can plug in this formula. This would be the probability of y given x and w times the probability of w. And we want to maximize it with respect to the weights. Alright, we can take the logarithm of this part, and since the logarithm is concave, the position of the maximum will not change. So I can take the logarithm of it here and the logarithm here. And so this would be equivalent to the previous problem. Alright, now we can plug in the formulas and try to solve the optimization problem. So we have the logarithm of the probability of w given x, of y given x and w, plus the probability, logarithm of the probability of w. We can plug in the formulas for the normal distribution and obtain the following result. So it will be the logarithm of some normalization constant c1 times the exponent of -1/2. So the mean is w transpose x, so this would be y minus w transpose x transposed times the inverse of the covariance matrix, so it would be sigma squared I inversed, and finally y minus w transpose x, and we have to close all the brackets, right? And in a similar way we can write down the second term, so this would be the logarithm of c2 times the exponent of -1/2, and this would be w transposed gamma squared I inverse w transpose, since the mean is 0. Alright, so we can take the constants out of the logarithm, and also the logarithm of the exponent is just the identity function. So what we'll have left is -1/2. The inverse of identity matrix is identity matrix, and the inverse of sigma squared is 1 over sigma squared. So we'll have something like this: y minus w transpose x transpose times y minus w transpose x. And finally, we'll have the term -1 over 2 gamma squared w transpose w. This thing is actually a norm, so we'll have a norm of w squared. This is w squared, and this is also a norm of y minus w transpose x squared. So we try to maximize this thing with respect to w. If we multiply it by -1 and also to sigma times 2 sigma squared, we'll come to the minimization problem from the maximization problem. And finally the formula would be the norm of this thing squared plus some constant lambda that equals to sigma squared over gamma squared times the norm of the w. squared. And since we multiplied by 1, it is a minimization problem. So actually, the first term is sum of squares. So we solve the least squares problem. And the second term is a L2 regularizer. And so by adding a normal prior on the weights, we turn from the least squares problem to the L2 regularized linear regression.